Welcome back to Calculus. This lecture goes along with Larson's Calculus 11th edition. Originally for Math 1411 at UTEP, Section 1.2. This is the formal definition of limits with Epsilon-Delta. And my name is Tuesday J. Johnson. Yes, Seahawks fan till the end. Go Hawks. So, some common types of behavior associated with the non-existence of a limit. The function approaches a different number from the right side than it approaches from the left side. And we saw that in the part 2 of the lecture, the graphical notation, where we had the limit as x approaches -2 of the absolute value of x plus 2 over x plus 2. The function increases or decreases without bound as x approaches c. So the function goes to infinity. And we saw that in the previous lecture with the limit as x approaches 1 of 5 over x minus 1. And sometimes the function just oscillates between two fixed values and it doesn't settle on anything. This frequently occurs with trigonometric functions. So now the formal definition of a limit. Let's let f be a function defined on an open interval containing c, except possibly at c itself, so c may not be in the domain, but everything around c is in the domain of f. And let L be a real number. This statement that we've seen before, the limit as x approaches c of f of x equals L, means that for each epsilon greater than 0, there exists a delta greater than 0, such that if x minus c in absolute values, so the distance between x and c, is positive because it's a distance, but is less than delta, then the distance between f of x and L will be within epsilon. This is known as the Epsilon-Delta definition of a limit. So if we're within a certain tolerance for our measurements, our output will be close enough, whatever we decide for epsilon, our output will be close enough to the limit. Here's a graphical version. If we're given an epsilon value, maybe it's 0.5, maybe it's 0.1. Looking at our function, how does that correspond? How close do I have to be in terms of delta? This would be the delta value I would choose. As long as I'm within this range for my x values, my y values will be within the required epsilon. So epsilon delta according to a graph. So let's do some examples. We're going to find the limit L, either graphically or numerically. Then we're going to find the delta necessary so that the function is within 1/100th of the limit as long as x is close enough to delta. Let's start with the limit as x approaches 2 of 3x plus 2. Here I've graphed 3x plus 2. As x gets closer and closer to 2, my y values become 8, and that's my limit. Now that I have my c, which is 2, my L, which is 8, and my f of x, which is 3x plus 2, I can start with my epsilon delta definition. So let's start with f of x minus L is less than 0.01. And we're going to make our substitutions. Replace f of x with 3x plus 2, subtract. The limit L is 8, still in absolute values, still less than 0.01. 3x plus 2 minus 8 simplifies to 3x minus 6 is less than 0.01. And if I factor a 3 out of the absolute value, and I'm factoring out a positive 3, so it's all good. Factor out a 3, and I'm left with absolute value of x minus 2 is less than 0.01. Check it out. 2 is our c value. That's what we're looking for. We're trying to simplify this to a form of the absolute value of x minus 2, c value. And that's what I have. To get the absolute value of x minus 2 by itself, I'm going to divide both sides of this inequality by 3. Since it's a positive 3, my inequality remains the same. The absolute value of x minus 2 is less than 0.01 over 3. Yes, that is an ugly fraction. We don't normally mix decimals with fractions, but we're going to go with it today. That's our delta. Our delta has to be a third of our epsilon in order for this limit to be true. So our x values have to be super close to 2 if we want our y values to be within 100th of 8. All right, another one. Here, The limit as x approaches 5 of x squared plus 4 equals 29. Why is that? X squared plus 4 is graphed. As x approaches 5, my y values are 29, the line right before 30. So graphically, I can find this limit. And now, our goal is we want to end up with x minus 5 is less than delta, and we'll find what delta is. And we want to start with the absolute value of f of x minus L is less than 0.01. I know my limit is L. I know my C value is 5, so I get us started. Over here, absolute value of f of x minus L is less than 0.01, straight from our instructions. Replace f of x is x squared plus 4, minus, our limit is 29, still in absolute values, less than 0.01. X squared plus 4 minus 29 is x squared minus 25, still in the absolute values, still less than 0.01. But now what do? X squared minus 25, and keep in mind your goal. Always nice to know where you're going with this. It's, since I want my x minus 5 in absolute values, and I have a difference of squares, I'm going to factor the difference of squares. But I'm going to keep both of them in absolute values so I can make sure I don't mix up my signs on accident. Alright, so we left off at the absolute value of x minus 5 times the absolute value of x plus 5 is less than 0.01. Let's go back to our goal. Our goal is to isolate the absolute value of x minus 5. Now, we can divide by the absolute value of x plus 5, which will first be non-negative. And second, as long as it's not 0. But where is this 0? X plus 5 is 0 at negative 5. We're looking near 5. We are nowhere near negative 5. Near 5, it's not 0, and it's at most 11. Why 11? Near 5 is 6. Near 5 is also 4. But I want to make it more exact, so I'll go over estimate. 6 plus 5 is 11. That's the most I would say this would be. So when I divide both sides by the absolute value of x plus 5, I might even throw in a 6 here. 0.01 over 11, that works. 0.011 over 10 works if you wanted to put a 5 in there. Many different answers would work. This one is better because it's a smaller estimate. So if you're more exact here, you're guaranteed to be close to where you want to be for your limit. Find the limit L, then use the Epsilon-Delta definition to prove that the limit is in fact L. The limit as x approaches negative 3 of 2x plus 5 equals negative 1. Alright, let's see. 2x plus 5, as I get closer and closer to negative 3, it looks like the graph is indeed negative 1, so I've found my limit. Keep your goal in mind. I want to transform the absolute value of f of x minus my limit negative 1 less than epsilon. In general, we don't have a specific value. We want to transform it to the absolute value of x minus a negative 3 is less than delta. So let's try it. F of x minus a negative 1 is 2x plus 5 minus a negative 1. Minus a negative 1 gives us 2x plus 6. In absolute values is less than epsilon. Again, we'll factor out the 2. 2 is positive, so it's all good. 2 times the absolute value of x plus 3 is less than epsilon. And when I divide both sides by 2, the absolute value of x plus 3 is less than epsilon over 2. So it depends. How close do you want f of x to be to negative 1? Epsilon. You could tell me that number. I want it to be within half a foot. I want it to be within 3 millimeters. I can tell you how close your measurements need to be to negative 3 as long as we know how close we want to be to negative 1. So in general, we could use the epsilon, whereas in the previous examples we were using a specific value, 0.01. Find the limit as x approaches 4, the square root of x. Let's see, here's the square root of x. As x approaches 4, look at that, the limit is 2. So let's give our Epsilon-Delta an attempt. Starting with f of x minus L, replace f of x, square root of x, replace L with a 2. I'm looking at the square root of x minus 2 is less than epsilon. So now we're going to go opposite of factoring. We're going to multiply by the conjugate on both sides. And a conjugate of a binomial changes the sign in the middle, so what was subtract now becomes addition. The reason we do this, use the conjugate, is because of the difference of squares formula. But remember, if I'm going to multiply by the absolute value of square root of x plus 2 on the left, I have to also multiply by it on the right. Because this is absolute value, this will be a non-negative number, so our inequality remains the same. When I multiply the square root of x times the square root of x, I get x. Square root of x times a negative 2 and square root of x times a positive 2 combine to give me 0. Positive 2 times negative 2 gives me a negative 4. So on the left, I have the absolute value of x minus 4 is less than epsilon times the square root of x plus 2. The left side's awesome. That's exactly where we're going, right? We want to know how close x has to be to 4. The right side needs some work. So let's take a look at the right side. Near 4, right, because that's where we're looking, the square root of x plus 2 is super close to the square root of 4 plus 2. Square root of 4 is 2. 2 plus 2 is 4. Absolute value of 4 is also 4. So we can finish this off with our delta is 4 times the size of epsilon. So if epsilon has to be within a tenth, our delta has to be within 4/10. If I want the square root of x to be within 2.1 or 1.9, right? 1.9 to 2.1, a range around our limiting value of 2. That means that my x values have to be between 3.6 and 4.4. One more time, this one's straightforward. The absolute value of x minus 6. As x approaches 6, I have a y value of 0, my limit. So f of x minus L in absolute values less than epsilon. I'll replace f of x with the absolute value of x minus 6. I'll replace L with 0. How does that simplify? Well, it simplifies to the absolute value of 6 is less than epsilon. So my original function is simplified to my domain portion, absolute value of x minus 6. Delta equals epsilon in this particular case. Once again, a shout out to Desmos.com and their free online graphing utility. All my graphs look really good because of them.